All right. The final type of improper integral that we want to look at are integrals in which we are trying to integrate over all real numbers. In other words, and there's a typo here, I apologize, that should be from negative infinity to positive infinity, right? So if we look at something like this, let me just go ahead and paste this over here just so you can see what this function specifically looks like. If we were trying to integrate this from negative infinity to positive infinity, we have a bit of an issue initially because those bounds continue to increase or decrease, right? So how would we do this? And the idea here is that we are just going to have to split this up into two different limit statements because we can't take a single limit to two different values. So we're going to split this up into two separate integrals. And that split occurs at a convenient value or a place where it's pretty easy to split it up. It's typically 0, but if there is a vertical asymptote somewhere within the bounds of our integration, then we would use that value where the vertical asymptote occurs. So looking at something like this, so we're trying to find the area underneath this curve from negative infinity all the way to positive infinity. We're going to go ahead and split this up. And we're going to split this up as the following. We're going to say, all right, let's look at this from negative infinity and to 0. So that's where the split's going to occur of 1 over 1 plus x squared dx. And then we're going to look at this from 0 to positive infinity of 1 over 1 plus x squared. And as is the case when we are dealing with improper integrals, we're going to rewrite this as limit expressions or limit statements. So we're going to then say the limit as a approaches negative infinity from a to 0 of 1 over 1 plus x squared, right? So we're looking at this as the lower bound is negative infinity, plus the limit, this time again, we're using a different variable or constant here from 0 to b of 1 over 1 plus x squared dx. So now we're ready to integrate this. So we've got the limit as a approaches negative infinity, and the integral of 1 over 1 plus x squared, well, that's just arctangent of x. And we're looking at this from a to 0. And we're going to do the same thing over here, positive infinity, arctangent of x from 0 to b. And now we're ready to plug in, see what we have here. Okay, so if we plug in 0, the arctangent of 0 is just going to be 0. If we plug in a, that's where we're going to need our limit. So we're going to need to find a limit of this, of arctangent of a. And if you want, you can just skip that step too and just go straight into the evaluating the limit, but I'm going to write them all out. The limit as b approaches infinity of arctangent of b minus the arctangent of 0, which we know is 0. Okay, so this is just effectively 0 minus the limit as a approaches negative infinity. So for what angle is tangent going to approach negative infinity? Well, that happens at negative pi over 2. So we got negative 0 minus, this is negative pi over 2. And if it makes your life easier, I'll just write that 0 there so we don't get too confused. All right, now the limit of arctangent of b as b approaches positive infinity. So at what angle will tangent approach infinity or positive infinity? That happens at pi over 2. Minus 0. So we've got positive pi over 2 plus another positive pi over 2. And so we've got pi. There is our integral. So this integral also converges to a finite value, which paradoxically is just one of the things I love about calculus here is that we have an infinite area technically, right? The function is continuing to move towards both positive and negative infinity. So this area is constantly increasing. But what we're seeing is that it increases by such a small amount that over time, over these bounds, negative infinity to positive infinity, this area converges to a finite value. And this idea is something that we're going to explore a lot more as we start moving through series and start talking more about this idea of convergence.